Hello folks, how you doing? Today we're going to talk about earthquakes. And I'd like you to take a moment here and notice all of the time and effort I put into alternating every other letter here in italics to make it look like the word is shaking. Isn't that very cool? Yeah, thank you. Anyhow, so what is an earthquake? This is one of the things that we talk about, that everybody has some idea of what we're talking about. Some of the things I bring up, they'd be like, okay, sure, whatever. I kind of know what you're saying. But everyone's like, oh, yeah, earthquakes. Even though very few of us have actually been in an earthquake. And in any given year, not semester, but any given year, I might get one or two people raise their hand. Usually, again, they lived out California or something like that. Here in New York State, if you go up north enough, up towards the Canadian border, there's some activity up there, as you'll see the end of this slide. We do have some East Coast tremblers every so often, but nothing too significant. But again, everyone just, wow, yeah, you know what an earthquake is. I suppose we have Hollywood to thank for that. But so official science class kind of definition, we've got sudden trembling of the earth caused by the release of accumulated energy in rocks. And we call that energy seismic energy. You're going to see the word seis over and over and over again. Seismologist, someone who studies earthquakes. Seismogram, piece of paper that has the squiggly lines on it. The seismograph, the machine that makes it. Seismic energy, the wavelengths. They use this seismic over and over and over again. So whenever you see that word in any, say any context, even Seismosaur, that giant dinosaur, because he causes an earthquake when he steps, I guess is what they were going for there. Just think earthquake, okay? So there's a couple ways to get earthquakes. One is plate movement. Plate tectonics, the continental plates, and oceanic plates as well, I suppose, sliding side by side one another, all right? And that's the majority of the ones that you've ever heard of. And then settling. Well, settling is kind of what we see over by us. We don't have any plate boundaries on the east coast of North America. The closest one is in the middle of the Atlantic Ocean, okay? But as I said, we do have some earthquakes. One of the worst earthquakes we've ever had in North America was through Missouri, I want to say. It's the New Madrid Fault, at any rate. I want to say it was Missouri. And again, nowhere near our plate boundary, but these old ancient lines, every so often they settle a little bit, like a house, an old house. For no apparent reason, it creaks and groans periodically, and that happens with the earth as well. And I don't want to give you the nowhere is safe kind of idea, but, it is possible to have an earthquake anywhere. But they do tend to cluster in certain areas, as you'll see. So, you heard of the Ring of Fire when we talked about volcanoes, unless it's some odd semester when we are doing earthquakes before volcanoes. But typically you hear about Ring of Fire. Then it's the basically the Pacific Rim, okay? All the way around Asia, down through the Pacific Ocean, down to Antarctica, back up South America, North America. That whole area there is what we call the Ring of Fire, and that's where the majority of the world's earthquakes and volcanoes occur. And if you remember, second most commonly occurring place was the Mediterranean. Okay, the area around the Mediterranean there. But in general, we tell you that earthquakes, as we said, can happen just about anywhere. Here is that Ring of Fire, and every other plate boundary for that matter. So you see what I said over here in the East Coast? We've got no boundaries. Here is the seam for our plate, and it goes all the way across. And it cuts through California here, and that's why California has so many problems. All the way around over here, and yikes, there's just a bunch of little plates. This area is a mess. It really is. Red dots are volcanoes, pretty sure on this map, and they don't really acknowledge earthquakes, but you'll see that there's certain types of plate boundaries that are more prone than others. But this area in general in the Pacific, this is your home area over here. You know what I'm telling you already. Okay, it's just always something going on. Always something. Okay, 2 words to keep straight. And I have to say, as a student, I always had a little trouble myself with these. Okay? But you won't, right? Because I'm such an awesome teacher. So you're going to learn them and always remember them. Focus and epicenter. All right? You have, typically you hear about the epicenter because that is the geographic location. That is the name of the city, or 30 miles outside of said city. Okay, that is the surface. The focus, and if you think about it, it does make sense. The focus is where the earthquake actually occurs. Okay? It's the pinpoint. It's underground at the fault. A fault, we didn't define fault. Fault is a break in the rock. All right? Fault is a break in the rock. So, at any rate, focus, epicenter, keep them straight. What they'll typically say is, outside the city of Los Angeles today, we had a 4.5 on the Richter scale earthquake. It occurred at roughly 30 meters below the surface. Okay, that 30 meters below the surface is the focus. The outside of Los Angeles is the epicenter. And this line here marks that fault that we talked about. It's a break in the rock, okay? Be it a plate boundary or one of those ancient seams that I talked about. Seismic energy, okay? I just clapped my hand. Hopefully I didn't startle you too much. That's a sound wave. Everybody knows sound waves, okay? It's really helpful and easy to think about sound waves and seismic waves. Seismic energy is the same thing. All right? I clapped my hands. That sound traveled through the air, met your ears. The rock breaks or rumbles past itself. It releases energy waves. Those move through the rocks and are received. Okay, you follow? We're going to acknowledge 3 kinds of waves in here in this class. Your textbook goes on. They might talk about love waves and some other vocabulary words. We're going to keep it fairly simple here and just talk about P waves, S waves, and what I call Raleigh waves, or Rayleigh. I say Raleigh. So P waves, S waves, and Raleigh waves. So as I said, the energy is released inside of the Earth, and as it travels through, we call that it's a body wave at that point, because it's traveling through the body of the Earth. Well, at some point, it's going to reach the surface. At that point, they call it a surface wave. So P waves and S waves are body waves, and a Raleigh wave is a surface wave. Okay? So let's talk about P. P stands for primary. It's called primary because it reaches the seismograph first. It reaches the seismograph first because it travels fastest. All right? This is all kind of relative, you got to understand, but there's different types of energy is what it boils. Excuse me, hiccups. What it boils down to. And I've got something to show you to describe what compressional versus the next one we're going to see means. So the energy in a compressional waveform, the energy travels parallel to the wave direction. Again, I've got a video here we'll show you. P waves are transmitted through solids and liquids. S waves, on the other hand, okay, they arrive second at the seismic station. That's because they move a little slower, and that's because their energy travels perpendicular. S waves, as it turns out, only travel through solids, not liquids. So if you were monitoring both sets of energy waves released from an earthquake, and they traveled through some water, the S waves would drop out, but the P waves would keep going. Implications are varied, but it's just a FYI. Okay. So what does this mean? I like the slinky idea. Let's see if this link actually works. All right, we're going to let this run a few times. Doesn't want to go large screen. There's a loop button somebody showed me once. Ah. We have to make it small first. Okay, well. So what we're looking at here, I know I've got this to loop before. See in the top how the wave is traveling, kind of like crack the whip. All right, you and your friend each have a piece of rope, and one person shakes it up and down, and oh, perfect! I stopped it at a great place. And you're familiar with that wavelength that travels through there. Okay, that is the S wave. That's how the S wave travels. That's the one. Okay. Now the P wave, on the other hand, we use a slinky for. Now you see how it's compressed here, spread out here, kind of normal here. What we're doing here is if you held your hands roughly, a couple feet apart with the part of the slinky in your left hand and the other part of the slinky in your right hand. So the slinky's stretched out, resting on the table in front of you perhaps. Okay, and you jiggled one of your hands, pushed it real quick towards the other hand. So you sent a shock wave through that slinky. There it goes. What's happening is that energy is traveling in the same direction that you pushed it. That's why it travels faster, okay? This one takes more time, more energy to go up and down, up and down, up and down. But what you'd actually see, if you could slow down, maybe if you're really bored, and you have a friend and one of you has slow-mo on your cell phone camera, okay, you should be able to see this. You should be able to see this. And I'm sorry, I can't find the looping button. Oh, hey, here we go.
In a longitudinal wave, the disturbance that makes up the wave is along the direction in which the wave travels. Longitudinal waves are also referred to as compression waves. In a transverse wave, the disturbance that makes up the wave is perpendicular to the direction in which the wave travels.
Slightly better at any rate. I'm going to grab...
In a longitudinal wave, the disturbance that makes up the wave is along the direction in which the wave travels. Longitudinal waves are also referred to as compression waves.
Let's see.
In a transverse wave, the disturbance that makes up the wave is perpendicular to the direction in which the wave travels.
One more link in here. Shrink the text a little bit so it fits nicely. Beautiful. And if you guys will excuse me for 1 second. Can't seem to get my... Alright, folks, and we're back. Sorry about that interruption. Okay, so surface waves. What happens, as I mentioned, is that eventually those body waves will meet, come to the surface, and when that happens, they can compound. And what happens is that as they mix together, they merge, they make this wave that not only travels forward and backwards, but up and down. and you combine both of those forces, because you're merging these things together, it slows down. And believe it or not, the slower something like this goes through you, the worse it is. You get either of the previous two waves, and they zip through you. You might, oh, geez, what was that? Okay, but think about if it just grabs a hold of you and shakes and shakes and shakes. Okay, that's what happens with these Raleigh waves. These cause, the most damage. The initial rumble, okay, from the earthquake might rattle some things loose here and there, but once that energy gets to the surface, that's when the real damage starts. And it's not a huge amount of time in between, okay? It's hard to separate it, when you're actually in the event. But this is what causes, they call it ground roll, but if you've seen, and again, we have Hollywood probably to thank for this, that suspension bridge, zipping up and down in the air, again, like someone's playing crack the whip with it. That's, unfortunately, these Raleigh waves really do a lot of damage. So it'd be nice if this was animated, but it doesn't. So it shows you that the wave moves up and down, so it's going to shake you this way, and then it goes through you this way as well, and it just messes a lot of stuff up. All right. So anyhow, moving on. Scientists, scientists, they love to measure things, right? And over the years, we've had a couple different ways. Two of the ones that have stuck around are the MERCALI and the Richter. And the Richter is what you're familiar with. When you hear a number, a 3.4, a 7.6, whatever. And typically they say on the Richter scale anyway, so you know it's a Richter scale. But that is the preferred method. That comes directly from the seismograph. It's wired into the bedrock, the solid rock, and as long as they're kept, calibrated, taken care of, every seismograph in the world reacts the same way to the same stimuli. And that's exactly the way scientists like it to be, okay? That way, a 3.4 in Africa is the same as a 3.4 in Russia, is the same as a 3.4 in London, is the same as a 3.4 in US of A. It's always the same thing. This is what we do an exercise with the virtual earthquake. You'll see it's very cool, and it gives you an idea how this all works out. The MERCALI scale, on the other hand, is much more human. It's qualitative instead of quantitative. Quant is numbers and measuring. Qualities, okay? Well, in science, qualities are kind of subjective, and that's kind of a bad thing. I think we got a MERCALI, yeah, right here, okay? MERCALI scale would tell us that, let's look at a MERCALI 5 here. Most people felt it. Some windows broke, some dishes maybe fell off, tall objects may fall over. Number 3 here, felt indoors but may not be recognized as an earthquake. This is, oh man, did you feel that? It must have been a large truck went by. Oh, there it actually says, vibrations like a large passing truck. A 2, okay, if you're just sitting there in your chair or laying in bed on a high floor, you might feel the rumbling, but somebody, out downstairs doing the dishes or something like that might not notice it. Okay, all the way up to, it's very descriptive. Okay, you could read it. The problem is people are excellent storytellers is the problem. Some people exaggerate, some people under-exaggerate, some people tell it just like it is. And the problem is that's very hard for scientists to compare notes. Okay? Damage is also not great because not all buildings are made the same. when I was telling you about a 3.4 in Africa versus a 3.4 in London versus a 3.4 in China or San Francisco, okay, the buildings in some of these areas are built significantly differently than some of the other areas. And a 3.4 may not have the same effect, you follow? May not have the same effect on a city or a town as it may somewhere else. That's the problem with MERCALI. And again, people, not just watching damage. Someone might come out and say, "Oh my God, it was so horrible," and then you know, you interview their neighbor, and some big macho guy says, "Oh yeah, I didn't feel anything." You know, in fact, maybe he was hiding in the basement crying. You don't know. Okay, so MERCALI's tough. Richter, how tall did that wave go on the piece of paper? How quickly are they? How closely are they packed together? It's much better. All right. So Richter scale. All right, measures the seismic energy released, measures the amplitude or the height. Okay, and the thing to know about this is that let's separate that because they're not really related. When we jump from a 3 to a 4 or a 4 to a 5, it's a logarithmic increase, which means it's a 10 times jump. A 4 is 10 times worse than a 3. A 5 is 100 times worse than a 3. Okay? And that's not a scale we're used to. Usually you're in class, 90, 80, 70, 60 is your grade scale. Excuse me, grade scale, right? Well, that's a little different, okay? It's like moving, like skipping every other letter, maybe, and moving from a, no, that's a horrible example, but any rate, it's 10 times worse when we jump from a 3 to a 4, okay? Not just a little worse. So, speaking of worse, what have we had? I haven't updated this in a while, but I don't think we've had anything to update it with. I remember this one, unfortunately. This was Christmas night or the day after Christmas. It's 2004. Many of you guys were a little young to be paying attention then. You older folk like me might remember this one. And it was over in Java, Sumatra area there. And it was an island, you know. It was, they had a tsunami. Tsunamis are caused by earthquakes. It was horrible. Lots and lots and lots of people killed. I don't even know if they're Christian and had Christmas over there or not. I don't know. But just a horrible thing to have happen so close to Christmas, let alone any day. You know, don't get me wrong. But it was all in the news and everything. It was rough. So 9s, okay. 8s, 7s are bad. You will definitely hear even these cities that are built to withstand some hurricanes, some earthquake damage. 7 and 8s are bad enough. 9s are devastating. Actually, I need to look and see. There was one fairly recently. I got to check and see what, like last year, kind of recent. Might have been a 7 something. But these 9s, we haven't had a 9 in a while, thank goodness.